Welcome to this comprehensive guide for Section 3 of the Databricks Certified Data Engineer Associate Exam by Data Operations Guy. In this presentation, we'll cover data processing and transformations, focusing on the new exam version that became effective after July 25, 2025. This section is crucial for understanding how to effectively process and transform data within the Databricks platform. Section 3 covers 5 key topics that are essential for any data engineer working with Databricks. First, we'll explore the Medallion architecture and its 3 layers: bronze, silver, and gold. Next, we'll discuss cluster types and configuration for optimal performance. We'll then examine Delta Live tables and their advantages for ETL processes. Following that, we'll cover DDL and DML features in Databricks. Finally, we'll learn about computing complex aggregations with PySpark DataFrames. Our learning objectives include understanding the purpose of each layer in the Medallion architecture, selecting appropriate cluster configurations for different scenarios, recognizing the advantages of DLT for data pipelines, implementing DDL and DML operations in PySpark, and computing complex metrics using PySpark aggregations. The Medallion architecture is a fundamental data design pattern used in Databricks to logically organize data into layers based on quality and refinement. This architecture consists of 3 main layers. The bronze layer serves as the initial landing zone for all raw data, ingested as is from source systems with minimal or no transformations. It acts as a historical archive providing data lineage and auditability. The silver layer contains cleaned, filtered, and conformed data with basic transformations, schema enforcement, and data quality checks applied. This layer provides a single source of truth for business entities. The gold layer represents the final, highly refined data optimized for business intelligence, machine learning, and advanced analytics. Data in this layer is aggregated, enriched, and presented in formats that directly serve specific business needs. The advantages of this architecture include improved data quality as data progresses through layers, enhanced data governance with clear separation of concerns, flexibility for schema evolution, performance optimization for different access patterns, and auditability through the preserved raw bronze layer. Databricks offers various cluster types to optimize performance based on specific workloads. All-purpose clusters are designed for interactive data analysis, exploration, and development, allowing multiple users to share resources. Job clusters are optimized for automated jobs like ETL pipelines and scheduled reports, with Databricks terminating them after job completion for cost efficiency. High concurrency clusters provide enhanced isolation and performance for multiple users querying simultaneously. Serverless compute, which is recommended where available, allows Databricks to manage the entire infrastructure, simplifying operations and optimizing costs. Key configuration parameters include autoscaling to automatically adjust worker nodes based on workload, choosing appropriate instance types for driver and worker nodes, enabling Photon Engine for SQL and DataFrame operations, using Delta caching for faster data access, monitoring CPU utilization targeting 70 to 80% for cost efficiency, and watching memory usage to prevent errors. For scenario-based optimization, use all-purpose clusters with autoscaling for interactive development, job clusters sized to match workload for ETL and batch jobs, carefully sized clusters with appropriate minimums and maximums for streaming workloads, and GPU-enabled instances for machine learning training. Delta Live Tables, or DLT, is a declarative framework within Databricks that significantly simplifies ETL development and management. DLT offers several key advantages over traditional ETL approaches. First, it enables declarative pipeline development where you define transformations using SQL or Python, and DLT automatically orchestrates the execution graph, reducing complexity and making pipelines easier to build and maintain. Second, DLT provides automated ETL and orchestration, handling task orchestration, dependency management, and error handling automatically without requiring external schedulers. Third, it includes built-in data quality and monitoring through expectations that allow you to define data quality rules directly within pipeline code, with DLT monitoring these expectations and handling invalid records appropriately. Fourth, DLT offers simplified error handling and recovery, with robust mechanisms that can automatically restart from failure points. Fifth, it provides cost-effectiveness through serverless compute and automatic resource optimization. Sixth, DLT supports both batch and streaming data within the same pipeline, enabling unified solutions. Finally, it automatically tracks data lineage for governance and compliance purposes. Implementing data pipelines with Delta Live tables follows a structured approach. The implementation process involves 4 key steps. First, define tables declaratively using SQL or Python to specify transformations and dependencies implicitly through table references. Second, add data quality expectations by defining rules that DLT monitors to handle invalid records appropriately. Third, configure pipeline settings including target schema, storage location, and cluster configuration for optimal performance. Fourth, deploy the pipeline and monitor its execution through the DLT user interface, viewing data lineage, quality metrics, and performance statistics. Key features of DLT include support for both batch and streaming data, automatic schema evolution and validation, and built-in monitoring and observability. The declarative approach means you focus on what you want to achieve rather than how to achieve it, with DLT handling the operational complexities automatically. Databricks provides comprehensive support for both data definition language and data manipulation language operations, enhanced by Delta Lake's ACID properties and schema evolution capabilities. DDL operations include create table for creating new Delta tables with schema, partitioning, and properties, alter table for modifying schema or properties of existing tables, and drop table for deleting tables and their data. DML operations include insert into for adding new rows to tables, update for modifying existing rows with transactional consistency, delete for removing rows from tables, and merge into, which combines insert, update, and delete operations into a single atomic transaction, commonly used for upserting data. PySpark integration provides a programmatic way to interact with Delta Lake tables, allowing DDL and DML operations using Python code. While SQL commands can be executed directly through Spark.sql, PySpark DataFrames offer more flexibility for complex data transformations before writing to Delta tables. This integration enables seamless transitions between SQL and programmatic approaches based on your specific needs. PySpark DataFrames provide powerful capabilities for computing complex aggregations and metrics on large datasets. Basic aggregations use group by and AGG functions, with common aggregation functions like count, sum, average, min, max, collect_list, and collect_set. You can perform single aggregations by grouping data and applying one function, or multiple aggregations by applying several functions simultaneously. Window functions enable advanced analytics by performing calculations across sets of data frame rows related to the current row. These include ranking functions like row_number, rank, and dense_rank, analytic functions like lag, lead, first, and last, and aggregation functions like sum, average, min, and max applied over windows. Window specifications define partitioning and ordering criteria, with frame boundaries controlling which rows are included in calculations. Performance optimization techniques include leveraging Spark's lazy evaluation by building chained transformations, minimizing data shuffling through optimized operations, using appropriate data types for efficiency, and caching data frames for repeated operations. These techniques ensure efficient processing of large-scale data aggregations. Let's summarize the key takeaways from Section 3. The Medallion architecture, with its bronze, silver, and gold layers, provides a structured approach to data quality and organization in Databricks. Cluster configuration should be optimized based on workload type, with different approaches for interactive, batch, and streaming jobs. Delta Live Tables simplifies ETL processes with declarative syntax, automated orchestration, and built-in quality controls. PySpark provides powerful APIs for complex data transformations and aggregations with both SQL and DataFrame interfaces. For exam preparation, expect questions on identifying which Medallion architecture layer is appropriate for specific tasks, selecting optimal cluster configurations for different scenarios, understanding DLT advantages and implementation, performing DDL and DML operations in both SQL and PySpark, and writing code for complex aggregations using group by, AGG, and window functions. Focus on practical applications rather than just theory, as the exam tests your ability to solve real-world data engineering problems using Databricks. Study resources include the official Databricks documentation and Databricks Academy courses. Remember that hands-on practice with the platform is essential for exam success. This concludes our comprehensive overview of Section 3, Data Processing and Transformations for the Databricks Certified Data Engineer Associate Exam. By mastering these concepts and practicing with real-world scenarios, you'll be well prepared for this section of the certification exam. Good luck with your studies and certification journey.